Good morning, everyone. My name is Hector Marco. I'm going to present a work related with ASLR, how to bypass ASLR and all this stuff. So first of all, who we are. My name is Hector Marco again. I'm working as a lecturer in the University of the West of Scotland. Okay, this is a collaboration research work between UWS and UPV in Valencia. So I am from Scotland, so I'm a lecturer in Scotland. And Ismael is working as cybersecurity researcher too in Universitat Politécnica of Valencia, Spain. Okay. Well, a little bit about us. In order to summarize a little bit our findings, I just put some lines here. So we have made some contributions to the Linux kernel, to the library, to the glibc library, as many other open source code. Some of them were rewarded by Google, Packet Storm. Okay, I was here 2 years ago, Black Hat Asia 2 years ago, DeepSeek, also 1 or 2 of them. So we have reported multiple CVEs numbers. Maybe some of you remember one of these two is the root shell. Okay, this enter key for 70 seconds. Do you remember that? So we were the ones who discovered that. Maybe some of you also remember about the group 28 vulnerability. Again, so if you backspace 28 times, and then a drop shell will appear. So, okay, so this is one of the two most known, but obviously we have more than that. Okay, we have basically working on low-level security. We found also vulnerabilities, maybe they are not as popular as the group or root shell, but for example, Linux kernel integer overflow was a vulnerability in the Linux kernel, but affecting basically the quality of the entropy of the executables when they were loaded in memory. Okay, the vulnerability was present since the very first version of Linux. So we discovered that 2 years ago, more or less, and was present in the very first version of Linux. Well, to be clear, since the Linux supports 64-bit architectures, randomization for 64-bit architecture. Okay. We have also experience in low-level security. Maybe you have heard about Renew SSP. It's a new method or a new technique to prevent brute force attacks against the stack smashing protector. Okay, so this is a new technology. Let's say ASLR next generation is also is a series of patches, Linux patches that, as far as we know, is the best implementation, the best ASLR implementation. Okay, providing a lot of entropy. So it's not. So a little bit about us, okay? Low level, let's say background. This is the low level, okay? Because we are also doing cybersecurity research. We are also lecturers at the university. So we are doing plenty of things. This is part of more hacker thing. So talking about ASLR, as you can imagine, ASLR is a technology that is present in all modern systems, okay? It's in Windows, Linux, Android, iOS, everywhere, okay? It is a barrier that most attacks need to bypass, okay? Especially if we are talking about memory errors. When we are exploiting memory errors, we need to face against this, okay? Not only memory errors, okay? But especially. And then we thought, okay, we need to assess the effectiveness of the ASLR, okay? Let's see if ASLR is as hard as they say to bypass, okay? Maybe we can find some trick, something to bypass the ASLR, okay? So, and then we had, okay, let's see if we can find a generic method in order to bypass the ASLR in 64-bit architecture. So this was our goal. So the question now here is, can we do that? Can we create a generic method that we can reuse in multiple attacks, in multiple scenarios to bypass the ASLR in 64-bit architecture? Well, this talk is exactly about that. In this talk, I'm going to present Return to CSU, which is a direct method to bypass the ASLR in current 64-bit Linux, okay? In order to do the demo more attractive, I'm going to bypass also the stack smashing protector, the non-executable bit, the railroad, the PI, Fortify. So we are going to face against a full protected server, okay? And let's see how can we bypass all these protections, okay? And obviously the demo is around 1 second, 2 seconds. So we are going to invest 1 second, 2 seconds to bypass all these technologies, okay? So, agenda. Briefly, what is ASLR? I am pretty sure that you know what is ASLR, but maybe ASLR is not what you have in mind, okay? ASLR is it's not only one statical thing that is implemented. No, we will see in a minute which are the variants, which are the flavors of this ASLR. The second part, we are going to talk about which is the difference between the source code and the resulting executable file, because this is something that we are going to use to exploit this, okay? We will see the difference that when we are facing against an executable, we need to see which part came from the source code and which are not, and what is happening there, okay? The point here is that they don't match. When you're compiling a source application, the resulting ELF is not exactly what you have in the C file. So let's analyze this. So thanks to that, we find a way to create a method, a generic method, to bypass this ASLR, okay? We name that return to CSU, okay? In order to show you a little bit how can we take profit of these methods, we have modified Rupert, okay? It's a tool which generate auto-generation root chain tool, okay? So we have modified this tool to implement this attack, okay? I will show you in the demo, I will show you different demos, but one of them is this tool, this modified tool, which basically you just need to paste, okay, this is the IP of the server, and then the application, or in this case the tool, will create a Python, an exploit in Python that you can use against any server. So it's completely automatic, okay? So you don't need to do anything. Well, again, in the demo, I will show you how can bypass all these technologies, okay? Position independent code, ASLR, on execute. So it's like GCC, full protected. Okay, let's see. And also, I'm going to talk a little bit about mitigation, conclusion, why it is so difficult to fix that, what is not so easy to patch this problem, okay? So what is ASLR? If you go to Wikipedia, probably you will find a computer security technique for preventing exploitation of, well, that's definition. So I think no one is going to understand what is ASLR actually if you go and read Wikipedia, okay? You will find something like the stack executable will be randomized. But when? How? Which is the quality? So what is actually the ASLR? Well, it is a concept, okay? And Windows is implementing this concept in a way. Linux is implementing this concept in a different way. Even Mac is using a different implementation. So we cannot say, oh, this has ASLR, so I cannot bypass it. No, you need to study this particular target. You need to see, okay, which is the weaknesses, or how can we bypass this, okay? So in our case, we choose Linux because it's one of the most popular and to be honest, one of the most robust. Okay, you cannot compare the ASLR in Linux with Windows or Mac. Okay? They are far from the quality of Linux. Okay. So one of the huge differences is that, for example, in Linux and Mac, they are using per boot ASLR, which means that libraries and executable are only randomized when the system is booting. So at the very first boot. So if you execute any application, all libraries will be exactly at the same position. You know, you can execute one application and later on execute a different application, but they are sharing these addresses, this mapping, okay? So in Linux, no. If you execute an application in Linux, you can kill this application, relaunch the application, and the map will be completely different, okay? The map is that one. So this is the map, okay? So talking about Linux, what is doing Linux? How an executable ends in the memory layout and this is randomized. How this happen? Well, when you basically run an application, there is a module, a Linux kernel part, which instead of just loading this executable into the memory, what they're doing, okay, let's put in a random places because we have the full, let's say, the full virtual memory space. So let's randomize a little bit this. Let's start for these 4 things. There are much more, but you know this. Stack, so the stack is at some random place at the top, okay? The executable, if it is PyCompile, be careful with that because I think the recent versions from Ubuntu, they already use that, okay? But if you don't specify this flag compiler, then don't expect that the executable is randomized, okay? Because kernel can do magic. So the heap, if you are using randomize v space equal to 2, this is a Linux kernel configuration, then the heap will be also randomized, okay? So don't confuse because maybe you can see even a 0 here, or well, a 0, no, a 1. If you see a 1 here, means that the heap is not randomized, which means that it's joined to the executable. But because the executable is randomized, from outside, it looks that the heap is randomized, but actually it's not. In other words, if you know where the executable is, you know where the heap is. and in the opposite. Okay, so this is this value. So Linux basically is randomizing everything. If you put a 1 here, and additionally the heap is a little bit randomized from the executable if you put a number 2 here. Okay. So how libraries are randomized in Linux? Well, we are still in the kernel side. Okay. So basically, what Linux is doing is choosing a random value more or less between the heap and the stack. So for me, this is where the libraries will be loaded. Okay, so this is a random value. Okay, but there is no library. So what the Linux is doing is loads the dynamic loader. Okay, this is a library where, again, in the number that the Linux choose. And what happened? So jumps to user land. Okay, when we are compiling an executable and this executable is dynamically linked, then Linux transfers the control to this loader. So the very first assembler instructions executed in user land is not your executable. Okay, it's this dynamic loader. So if we are, for example, this is a dump using GDB, we can stop the application in the DL start, which means basically is almost the start symbol in this dynamic loader. And if we inspect the memory map exactly at that point, this is basically 1 or 2 instructions executed in the user land, no more. I think it's 1 move and 1 call, so there is nothing here. So you can see that we have 2 lines per file. For example, in this test application, we see read and executable and read and write. Okay? So, but there is no, where is the live C? The library C. There is no live C here. We don't have live C, okay? Because Linux is not the one who is loading everything for you, okay? This is done by the dynamic loader. This is the one who is loading objects here, okay? So the dynamic loader is who is loading libraries depending on your needs, okay? So now let's inspect the memory layout at the very beginning of the executable. So if you see here, now this start symbol is the start of the executable. So take a look and see the difference. Before we have only 2 lines, read executable, read write, but now we have only one with read, which means that the dynamic loader is the one who is responsible for protecting pages with read-only permissions. Okay, Linux is not doing that for us. Okay, this is just to show you what is actually ASLR, memory layout, and all this stuff. Okay, it's not just a static thing that you don't know who is doing what. Okay, but the point here is that libraries are loaded side by side here, but there is no more randomization. Okay, there is no one is doing more random things. Let's say. Okay, just putting libraries here side by side. But from outside, it looks, okay, this is a random value, okay? So just to do a comparison between ASLR in 32-bit and 64-bit architectures quickly, most of the people, if you ask why the ASLR is much better in 64-bit architectures, well, the fair answer will be, okay, Hector, because you have much more entropy. Okay, if you compare the entropy that we have in 32-bit architecture is only 8 bits, which means that 268 possibilities, you know. And if you compare this entropy with 64-bit architecture, you will see a lot, millions, okay? So, well, millions of options, millions of places where you can allocate your libraries, so that is much better. But this is not the only reason, okay? What about the ABI, the call parameters, okay? And this is important. I'm going to explain why. In 32-bit architectures, parameters are based on stack. So, and in 64-bit architectures, parameters are based in registers. And this is a huge difference. Why? Because, for example, attacks like return to libc or return to whatever are not possible in 64-bit architecture. Okay? And doesn't matter, it's not because the entropy is not, no. You can't jump to, for example, in return to libc, what the attackers were doing in 32-bit architectures is because they control the stack. Basically, they, for example, exploiting a stack buffer overflow, they are overwriting the stack. Because they control the stack, they can put the parameters they want and then jump, for example, to the PLT, okay, for system or any other entry in the PLT section of the executable. Okay, so this is no longer possible in 64-bit architecture, and it doesn't depend on the quality of ASLR or bit entropy or whatever. Okay. So, for example, the offset to lib, I don't know if many of you know offset to lib, is something that we also discovered and released some years ago. Currently, it's not possible. I am using the word partial here. I'm going to explain in a minute why it's partial offset to lib. Okay, you can't use offset to lib to bypass ASLR in 64-bit textures today. Okay, but we can use some of the ideas of this attack. Okay, to combine with this the attack I'm presenting today in order to achieve our goal. Okay, so summarizing, the ASLR in 64-bit system is not only better but faster. Why? Because I didn't mention, but we have support. The CPU have support for relative instruction pointer, okay? But we don't have this kind of support in 32-bit architecture, okay? So we need to do some call tricks here in order to know where we are and then to relatively access to data and all this stuff, okay? So if you can move to 64, you should do it now. So 64-bit architecture is much more secure by far, okay? And it's faster, okay? And again, it's not only a matter of entropy, but this ABI introduces a huge challenge, okay? So, when I'm saying that offset to lib attacks are partially possible, basically offset to lib was a practical ASLR bypass. It was a generic method, valid for multiple scenarios. But in 3 years ago was fixed. We sent a patch to the Linux kernel, and they fixed that. Okay, which basically means that now the executable is here, but not here. So before we sent our patch to Linux kernel, the executable was joined to the libraries. Okay, so once you know where is the executable, means that the libraries are in a constant distance offset. Okay, but we can use partially this in order to know where the executable is in memory. I will explain later on how. So basically, we need to find an alternative, okay? So we are looking for a generic method, okay, in order to be used this attack in any scenarios, okay? And must to be valid for 64-bit architectures, need to deal with ABI, call parameters, all this stuff. Okay, let's see what we can do, okay? So the first thing we did, okay, if we know where is executable, if we know that we can use it, and we need to deal with the ABI, with the call parameters, let's see which code will be always present there. So let's do an empty C file. This is an empty C file. Okay, it only contains one single line. Okay, and this is a return 0, which means it's doing nothing. But if we compile this, we will see that a lot of different symbols are already included somehow in our executable. But you know, I didn't put that. Wait a moment. My C program only had main. So what are these functions? From where? Who is putting that? Because this was compiled, this was linked, my application is dynamically linked. So what is going on here? So let's inspect the code. If we inspect the code, we will say that, okay, let's use object dump, and maybe we can read it. I don't know if you can read it from there. But there is an init function, a PLT entries here, some finalizers, but there are more code. We have the start. Who is putting the start? From where? This code. This is assembler code. We can abuse of it. Okay? The register team clones, another function, but more. Don't worry, there are more. Register team clones, another function, a lot of code here. Global destructors auxiliar, frame dummy. Oh, finally, we have our main function here. Wow. This is the return 0. Okay? Code. More code. Lib CSU init, as you can see here, a lot of code, more code. Fine, well, a lot of functions. So we have this source code application, but when we see the resulting executable, we have all of this, and only this small part came from our C code. Okay, so let's remove that. So let's put a name to that. So we have named this attached code. Okay? So for us, everything, apart from what the user can control, okay, what the compiler can, let's say, protect or touch, for us will be attached code. But who is attaching it? what is used for. So we start to ask questions. How protected is this code? So let's try to quickly answer these questions. Who is attaching this code? Well, we just did a script, and let's find everything about these functions, okay? And when we look, and we found is that all these functions are in that particular file, okay? These two functions is in this particular file. The start is in that file, and this is in that file. Well, but wait a moment. Theoretically, my application is a dynamically compiled application. So theoretically, why I am using libraries and object files? Theoretically, why? So this is the classical library that is used when you are compiling static things, and this is object file when you are linking things. So basically, we can say that this is the minimum static linked code that we will see when we are using dynamically linked applications, okay? So don't think that when you are using dynamic link application, everything is static. So, okay, now we know this code, but what is used for? Let's simplify it quickly. This is the exec-syscal flow, basically the Linux kernel. Again, when it jumps to the dynamic loader, what it's doing basically is calling some functions before main and after main. So basically, you can see this as a mechanism which allows us to execute code before and after main. Okay? Don't think that your main is the very first thing that will be executed. No, main is far, very far. Okay, is millions of years from the very first line executed at the user line. Okay? So we can use this attribute constructor in our C program, and then all these functions will be called before main. Okay? Same for destructors, finalizer, and so on. An example, very quick. We have our main function. Okay, here. This is the main function. As you can see, this main function is calling to at exit. Okay, but I don't have any at exit function here. Okay, I only have a function before, after main, my function at exit, only these three, okay? But I am not calling to any of these in my main program. If we compile this and we run this application, we will see these messages, okay? So the first printf is before main, is that one. So because we are using this attribute constructor. So how is possible that if we are not in the main calling to that function, this printf is how? Someone must to call this function before our main. Okay? Same happen after. You can use attribute destructor after main, okay? And you see before main, this is the printf, main, this is the main. Take a look. This is at exit function, but so far good. Main function at exit is that one, and after main is the last one. Okay? So somehow there are something there that is providing us this functionality. Okay? Let's go faster. So why it is attached to the executable? Why this code must to be in this executable? Okay, basically because in order to call these functions, we need to save the pointers somewhere, and these pointers are saved in the executable. And why we are saving these pointers or store these pointers in the executable? Because each application defines its own constructors, destructors, initializer, all this stuff. So it makes sense that these pointers they are stored in the executable. And in order to simplify this call to libc unit, they are attaching this code to the executable rather than other place. Because if they don't do that, the problem is that someone calling to that function, for example, if you are using the libc or any other library, will need to parse our executable to find this pointer in the executable. So, it's much more easy if you attach this code exactly there. Okay, so let's analyze this code. How protected is this code? So we just, let's see all these functions that we found in our attached code, and let's, for example, look for a stack smashing protector. So as we can see, we are compiling this empty file with a stack protector. All will means that all functions must to be protected using the stack smashing protector. take a look. Only the main function is protected. All the other functions that are in our executable are not protected. So this is telling us that these functions were already compiled, they are just linked. Okay? So PyCompile, so these functions are PyCompiled, this is good, but all these functions have no stack smashing protector, which is a problem. Okay? So how profitable is this code in a real attack? Okay, that's fine. We have some attached code, it's in the executable, but how can we abuse of this? Okay? Well, the first thing that you need to consider is that independently of the applications of code, we have always this code there. And it is not protected against a stack smashing protector, for example. Okay? So how can we abuse of this in a real practice attack? So this is what I'm going to explain in a minute, return to C0 attack. Okay? So this is let's say the steps, the recipe, in order to bypass the Aslr in 64 bits. So the first thing we did is let's try to use this attached code. Let's pass this attached code to automatic tools to see if they can find any drop, any gadget, something that is useful for us. Okay? Only considering this attached code. Okay? This will be printed. You can go home. You can check any application you have. And all this code will be printed always, okay? And you can do anything. You can't protect it. You can't. It will be there. You can touch it, okay? So we have used Roper, and the result, unfortunately, is that some of the necessary gadgets to build advanced rope attack were not found by this Roper tool, okay? Gadgets like write, what, where were not present, no control of some register, no syscall, okay? So it means that this code, is good, but, it's not as good as let's use automatic tool, okay? So let's use another application, another rope shell chain generator. So basically same problem, okay? They find we can control some registers, but there are not enough stuff here to build a real attack in practice, okay? So we are looking for something that we can use in practice. Okay, they fail, so let's see what we can do. So let's do a manual analysis of this attached code for fun and profit, okay? So the first thing we found is that there is something interesting in one of these attached code in a partial. At the bottom, we can see this, we can probably recognize this pop, 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 pop will look very good for us, okay? Basically, this gadget, we named this gadget 1. It's not bad. We are controlling some register, but unfortunately, the interested ones, the ones that are used to pass parameters to functions, we don't have the control of that. For example, RDI, RSI, RDX, we don't control this, okay? So not bad, but we are in the same situation that the automatic tools. Well, if we take a look to the second gadget we found in doing a manual inspection, we will see that there are some moves here, one call using this R12 and RBX, which means that we don't have the control. But if you see this end of this gadget, you will see that the registers we need here to control this call, these three, basically are using, because they are moved, are using these three. We don't control these three here, but we control these three in the first gadget. Okay, the first gadget, well, is not, Vector is not very interesting because I can't control this, the useful registers that I need. Well, let's save it for later. We can see, okay? So basically what this is telling us is that we can basically make a call, a control call, more or less. Okay, let's see what we can find from here. So this is in summary, we can jump to the very first gadget. We can do these pops, okay? And we can, again, change the control flow to the moves. And basically what we have in C code is something like this. Okay, we have like a function call with 3 arguments that we can control more or less, okay? So at this point we have a control call, okay, where basically we can control almost 3 registers, except the first, which is only 32, the 32 lowest bits, because this is not a R, it's a E, and we are using only the half of the word, okay? So we can jump where we want and control up to 3 arguments, not bad. So now the question is, let's analyze what we have. So in order to create a universal micro-ROP to control the execution flow, using of this, and considering only the attached code, the code that is not coming from the source code, okay? This is our current situation, okay? We have more or less a micro-ROP chain, but again, we don't have gadgets like write what where, which means, okay, I want to write this string in this portion of memory. We control 3 arguments, okay? But we can set some register to some values, but if we are looking for to call some functions, we can set this particular register to a particular value, but not the content. Okay, so we need to be careful with pointers. For example, we can put this number, but we cannot create this string or this multi-dimensional array string, okay, which is the second argument for the exec system call, for example. Okay, so we can control the flow. We can specify the destination of. Okay, I'm going to jump here, but we don't have some interesting registers. So let's see how can we escape of this and finally execute what we want. Okay. Again, we don't know where the heap, libc, or extract is in memory. Okay, so how can we create a method, a generic method from this? So let's review again, okay, this attached code. Okay, and so far we have a use of libc su init. Okay, only that. But we have much more attached code. So going faster because I am running out of time. We can use PLTs because they are very good candidates. Okay, you see how we need to call a PLT. It looks like a function call. Okay, PLTs are, as you can see, in the executable area, so means that is attached to the executable. And if we consider that a very basic application must to have read, write, or send and receive, because otherwise there is no way to interact with the application. So we can assume that or either read, write, or send, receive will be there, okay, or on it. This is just 2 examples, but some way to interact, okay, because if we cannot interact, it's hard to exploit, let's say. Okay, so assuming that this is a basic server calling to read and write, okay, so now we have our empty C file, but this empty file is calling to read and write, only these 2. Okay? Otherwise, we cannot even touch the executable. Okay, this is how PLTs looks. Okay, so basically, I did an abstraction. Is basically if we have write in our program, okay, means that there is a PLT entry. Okay, and this is basically the arguments they are expecting. Okay, if we match this, what we have, basically the very first argument is a file description. This is okay with us. The second argument is a pointer, so we can control the address but not the content, so 50-50. And the third argument is the number of bytes that you want to write. Okay, so this is fine for us. So the second one so far is the only one that is a little bit difficult. So let's see how we can abuse of this write. Okay, if we are able to call to this write, we can reduce the file descriptor in order to leak information to us. Okay? For example, we can call to write, and if we somehow are connected to a server, that means that this server internally is keeping a file descriptor associated to our connection. Okay? So if we write in this file descriptor, this message will arrive to us. Okay? So basically, the file descriptor is an integer that we can predict. Okay? This is trivial. So the most problematic one, we can put any value, but no pointers. So better say, we cannot control the content of the pointer. Well, we have the GOT table here, okay? And the GOT table is helping us a lot. Why? Because GOT table is an array. This array is in the executable area and contains its content are pointers to libraries, where the libraries are, okay? So basically, we can see this GOT as an array of pointers. So we can use here as a second argument where an entry, in this case, the number 1, okay? So this is the call we can do using the, let's say, the gadgets we have, okay? And this is a trick to randomize the libc library, okay? This is part of the attack. So if we somehow can, for example, assuming that the operating system return the number 4 as a gadget, as a file descriptor, and then we can write for God table 8, and this will magically send us the content of the God, okay? So basically, in order to leak where the libc is in memory, we are basically writing the address of this God table, which is in the executable area, okay? And therefore, the libc will be randomized, okay? So now the third parameter is 8, which means that please write 8 bytes using the file descriptor associated to my connection, and please send us the content of the very first entry of the God table, which is where is the write function is loaded in memory, okay? So basically, the server is sending us where this write function is located in memory. So we have the randomize where the libc is in memory, okay? So how can we build a final attack? Okay, now we have libc. This is trivial. Okay, it's trivial to generate any kind of full drop chain attack. Okay, and this basically is allowing us to execute arbitrary code. Okay, so we can see this attack, this return as two stages. Okay, the first stage basically is to create a micro rob payload to leak where this write is in memory, okay? And then attackers will receive where this libc is located in memory. Actually, where this write symbol is in memory, but write is a constant offset from the base where the libc is in memory. And the second stage is using this, let's create a full payload. This will summarize much better these two stages, okay? So the full attack is basically call to the gadget 1, okay, this is attached code, so this means that all of this is in the attached code, is in the executable, okay, this is the very first part, okay. So what we need is to redirect the control flow to the very first gadget, okay, and then to the second one, and then to the third. So the third is basically the PLT entry of write, okay. As a result, we will have where this write symbol is in memory. Okay, and this is the input of the second payload for the stage number 2. Okay, using this information, then we can start to jump to gadgets from libc as much as we need to create full functional rob attacks to do whatever we want without no restriction. Okay, at the end, I will show you how can we execute a remote shell. Okay, okay, well. More or less, it seems clear, but how can we know where the executable is in memory? This is the big question, okay? Because, you know, if I know where the executable is in memory, everything is. Well, again, you can use the offset to leap vulnerability, the weaknesses to guess that. But I would like to just present two things. If we are attacking a forking server and the executable is PyCompile, which means full ASLR, that means that we somehow need to do brute force attack, okay? If we are attacking a forking server and this forking server is not PyCompile, means that we need only one single shot to bypass everything, okay? So doesn't matter, but doesn't matter if you have canary or all this stuff, I will show you. If we have init server, which means that it's not a forking server, well, if it's not executable, again, one single shot, because we know where we need to jump, and we need how to create the stack, and we need to, you know, everything. So we can use this attack in all these scenarios. What about if we have an init server and it's executable? Well, question mark. We are still analyzing this. It's not that easy because we can't, we can't, let's say, guess where is the executable in memory by doing a small brute force attack. We can do, for example, partial overwrites of the return address without touching the full address, okay, in order to control and jump to the same executable, okay? But this is for another day, okay? So why automatic tools like Roper, Robshell fail? Okay, basically, they are so clever, okay, but as you can imagine, they have limitations. They are not perfect. So basically they are focused on profitable gadgets, okay? And then try to link them. Okay, this is a gadget, this is a gadget, this is a gadget. And as you can see, the gadget that was key for us is not a gadget, a typical gadget, pop, 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 return. It's pop, 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 call. And even this, sorry, move, move, boop, call. And even this move, move, boop is not, there is no relation. So it's hard to know that. So a better knowledge about which registers we control will improve this tool. For example, if the tools know, okay, I have no control of this register now, but there is a gadget in other place that I control and I can start to see registers and, it's not an easy task for an automatic tool. A lot of combinations, but manually it can be. So when an advanced ROP tools say there are not enough gadgets, well, it's not always true, as you have seen, okay? So I will suggest you to do a manual inspection of the code and see. So making this attack profitable, we have modified this ROPer tool to support this attack, okay? Basically, we extend this tool, and now it supports dup2, okay? And exec with these parameters, okay? In order to have an interactive shell. Okay, a minus symbol is missed here. Okay, basically, with your help, you will see that now you can use this tool. Well, I didn't publish the patch yet. I will do soon. Okay, and then you can automate this attack. So demo quickly. I'm going to show you how bypass all these things. Okay, not only the SLR. We are going to use a forking server, and this forking server is protected with all this technology. Okay, that means that it's PyCompile, libraries obviously with PIC, randomized VE space full, number 2, full stack protected all as much as we can. Okay, 64-bit architectures, real raw, now 45 equal to, optimizations. So the best executable you can give me now, full protected, okay? This is more or less what I'm going to show you, okay? So let's see how can we do that. Okay, I will show you a demo. First, okay, give me 1 second. I will move the screen. Yep. Oops. Where it is? One moment. Come on. Okay. I have here some exploits. I don't know how many time I have. Well, so this is the ROPer. So I need to wait to turn on the virtual machine. Let me see. I have Black Hat demo. Okay, basically this virtual machine is a regular Ubuntu virtual machine. And I'm going to run a server, a forking server, who basically is reading from a socket, okay, and writing back the answer. So let me. Okay, I'm going to run the. Okay, so somewhere virtual, okay. Okay. I'm going to move to root. Okay. Here, yes, we have here the server. I'm going to launch the server. Okay, this is a server, 64-bit architecture, pile compile, stack smashing protector, everything. Okay, I will publish the code and all this stuff. So let me. It's a little bit strange to me. Okay, here. Okay, now. So because I don't have too much time, I will go directly because I have two exploits. This is the first one is stage 1 return to CCU, which matches exactly with my explanation. Okay, the first one is just, well, maybe I have this 1 second. Stage, let's launch the very first exploit. Okay, server is VMware server. Port is 1999. Well, basically, the output means, okay, I'm going to find where is the offset of the canary, and the trick is send payloads, and every time you are sending a payload, you are increasing the payload until you will get a crash. When you get a crash, the connection is closed, and that means that you are touching something that is producing a crash, and this is the offset of the canary. Then we are guessing the canary value using a byte-for-byte attack, and we are using, again, the same trick from the offset to lib to guess where the executable is in memory using a byte-for-byte to the return address. And then we are using the gadget number 1 to leak where this write function, okay, this write function is in memory, okay? So basically, if we save this output, basically, as you can see, you can read from here, stage 1 output, this is the payload we need to introduce to the second stage, and this is the match the output stage 1 write. Okay, this is used by the other Python script. Okay, so let me. We can directly. I have combined both in full return to CCU script. So let's use it directly for the sake of time. Okay, full. Let's see. VMware server, and then the port 999. Okay, so the time it's real. So this is the time we need to bypass a forking server full protected. Okay, using this technique. Okay, this is real time. Count the time. So canary, everything, cell. Okay, now we are in a different environment. Take a look, you can see the server pi stack. You see the IP, for example. I don't know, it's not IP ADR. Okay, and we are root. Okay, this is the full time we need to bypass all of this. So like 1 second, 1.5 seconds, okay? All these stages, okay? So the best thing, this is generic. You can use it in any executable. So you don't need to care about, okay, maybe that these functions will be protected. No, they don't have a stack smashing protector. Or maybe this code is not there. No, this code will be there. If you can redirect the flow, you win. And this is how to do it in less than 1 second, okay? So going back to the presentation to talk about a little bit mitigation. Okay, let me 1 second, I need to go back to. Okay, so basically, with this attack, what we are basically saying is that if you have a forking server in the world and you have a stack buffer overflow, today you are lost. Okay, there is no way to protect that. Okay, if you find some server in the world, we have a stack buffer overflow, and you have the ability to perform a byte-for-byte attack, and then you can combine this attack, and you will get a root shell in 2 seconds. We are talking about more than 20 years old vulnerability, stack buffer overflows. Okay, And we are still trying to fix that. So let me show you the final conclusions. If this allows me, let me, 1 second. Why exploit proper? Okay, it's closed. Wait a second. Something is happening to my presentation. Okay, so let me see quickly. Okay, I plan to publish this in my personal website. Okay, in order to, it's not working. Okay, what I'm going to talk now is about some mitigations. I will talk about why it's so hard to fix and why we don't have. Let's do it without. Okay, yes, quickly about mitigations. Okay, mitigation one. One thing we can do is, okay, let's move some of these gadgets to the libc, to the library. So basically what we can do is to move some of this code that is attached to the executable. Let's move to the libc, okay? And then what we are doing is we are removing the gadget number 2 from our first, let's say, chain of gadgets. Okay, the stage number 1, we are removing that. Okay, we have implemented a patch to do that. This can be implemented, but again, we are removing only one gadget for a full chain. Okay, so the second is basically let's implement in a different way how the libc is managing all this stuff. And basically what we can do is to update or to change how this call is made, because this call, if you see the C code, is using a stack. We can use basically by adding the static word to the variables means that the variables, instead of using a stack, are using data, and then we are not depending on the stack. Okay, again, we are just destroying one of the links, so it doesn't look a very good solution. So a third solution could be to patch current applications. Basically, we have two flavors. We can, once we are in main, we are executing in main function, we can overwrite with zeros. So let's destroy this code, because I am 100% sure I don't need this code in the future. This have a problem with sharing resources, all this stuff. We have also implemented a patch you can achieve that. So you can download this patch, you can apply this patch to all executables, and more or less you are safer, let's say. The solution that we really want is to move this attached code to the libraries area. Okay? Why? Well, because if this code is there, we cannot abuse at all of this code. Okay? All executable codes will be user controllable, which means that there are code here that we cannot turn. If I am a developer, okay, I want this code to be secure. I want to compile this code with a stack smashing protector. You can do that. Okay, because this code is already compiled and this is in your executable. Okay, this solution is almost impossible it's very hard to apply. Basically, because this means move this to this will mean that the PLT and God must to be in library, and by definition, God is something that must to be belongs to the executable. Okay, it's not something that you need to share. So you can implement tricks, but it's not easy. Okay. And you can remove PLT, but then if you remove PLT, the way to call functions, library functions, is by accessing to the God table. But we also want to remove God. If we remove God, we cannot remove PLT. So there is no easy solution. So this is how we find it. Okay. So because sometimes people ask me, how do you find that? Well, sometimes you need to print assembler, and you need to study assembler. Okay. You can use your printer at home and spend, I don't know, 2 days reading line by line. For example, these were my notes. Okay, it seems that these are not useful, but maybe I can jump here, and later on I can jump there, and well, be careful with this. This is changing the control flow. So we were writing our own note to see, okay? But basically, you can print object and output and learn about that. Conclusions and black hats on white. Basically, we have presented a technique, a method that basically can automate the construction of exploits to bypass the Aslr in 64-bit architectures. Okay. To go beyond automatic tools, I always recommend to do a manual inspection, okay, because we have always rare gadgets, okay, and we saw that we can trust automatic tools, okay, by default. We present how we can create a micro rob to leak things. Okay, in this case, I use this micro rob to leak where the write is in memory, but you can use this micro rob to leak whatever you want. Okay, for example, passwords, any data in the executable, any buffer, local, whatever you want. Okay, imagination is the limit. Also, the attached code, be careful with that because invalidates other security techniques. For example, the instruction set randomization, which means that every executable is completely different. Okay, because you can randomize the instructions, or you can, change how they work. If you're attaching some code that you can't compile, you can't expect that it's protected or this is something with him, okay? So also security options must be decided at the very beginning. If you are attaching some code, you are linking some code, you can do that. Okay, we have presented some workarounds, okay, to prevent this gadget. You can use it, you can patch your executables to be safer, let's say. Okay, the ideal solution will be to move this attached code to the libc, but I saw that it's not a easy task. And that's all from my side. Any questions? Thank you very much.